Okay, I think we are ready to get started. Welcome to another Macron Group webinar. My name is Charles Zona, and today we are welcoming back Dalia Yablon. Dalia is going to talk to us today about measuring material stiffness and stickiness on the nanoscale with atomic force microscopy. But before we get started, I would like to give you a bit of Dalia's background. Dalia is the founder of Surface Car, an AFM consulting firm located in the Boston area. Surface Car specializes in surface and interface characterization, measurement, along with education and training focusing on scanning probe microscopy. Prior to Surface Car, Dalia spent a good portion of her career at ExxonMobil Research and Engineering, working with the chemicals division to develop new AFM-based imaging methods. Dalia is also the editor of the book Scanning Probe Microscopy in Industrial Applications, published in 2013 by Wiley Publishing. Dalia will field questions from the audience following this webinar presentation. If you have any questions throughout the webinar, just go ahead and type them into the questions field. As I mentioned, Dalia will be fielding questions from the audience after the presentation, and the webinar is being recorded and it will be available on the Macron Group website under the Webinars tab. And now I will hand the program over to Dalia.
Thank you, Chuck. Good afternoon, everyone. And today I'm going to go over some mechanical measurements with AFM, some of the more common mechanical measurements to measure stiffness and adhesion on the nanoscale. So I have shown this umbrella slide of AFM and all the different properties that it can measure in one of my previous webinars. As a brief reminder, I view AFM as really an umbrella of multiple modes, different modes that can characterize different properties of the surface, including mechanical properties, electrical properties, magnetic properties, and optical properties. Today we're going to be focusing on the AFM as a mechanical probe, and there are a number of different modes that can be operated in AFM in mechanical mode, and the one that we're going to focus on today is a mode called force spectroscopy, which we're going to look at in a little more detail to get at these two probably most common mechanical properties that are measured with AFM, which are the stiffness and adhesion. So again, the focus of today's webinar is force spectroscopy. So what is force spectroscopy, also referred to as force curves? These are simply single point measurements where the cantilever just goes in and out of the surface. It pokes the surface. So there are actually two different kinds of force spectroscopy type of measurements you can make. The most common kind is what's called static force spectroscopy. So you can see here we're plotting force on the y-axis versus lever sample distance on the x-axis. And this is what the traditional force curve looks like, where as the cantilever comes in, there starts to be some attractive interaction between the tip and sample. Then it snaps into contact. Along this repulsive wall, it's actually in contact with the sample, again called the repulsive or contact regime on the way in. Then on the way out, as we withdraw the tip, we're in contact initially. Then the tip kind of gets stuck in the surface in your material until it finally is able to pull out and reach its unperturbed state. Notice in this classic static force curve, there is hysteresis, so that the approach and the retract do not follow the same path. And there are 2 points of nonlinearity. One is a snap in and one is a pull off. So this is what we're going to focus on today. Just as an aside, there is a field called dynamic force spectroscopy, where you do the same kind of single point measurements with the tip going in and out, but now it's oscillating at resonance, and then you can measure the amplitude and phase as a function of tip sample distance. Here in the static force curve, we were just measuring force or deflection. But here when we're oscillating in resonance, we can measure amplitude and phase, and these can be used to probe phenomena like the attractive repulsive bistability in tapping mode, and also to probe the full interaction regime. I'm not going to speak any more about dynamic force curves today. Just want to make sure to give it a little bit of time so that we understand this is part of the whole force spectroscopy regime. But the rest of the webinar, we're going to focus on static force curves. So just to make sure that everyone is on the same page with the difference between force curves and tapping mode. So tapping mode is probably one of the most common imaging modes, where we oscillate the cantilever resonance and tap along the surface. And then these static force curves, we can create maps of them where we poke in and out, move to a new spot, then poke in and out again, just to make sure that we understand the differences between these two. So first of all, for force curve mapping, there are a lot of different names for it on the market now. These are just some of them. And this is a non-resonant, low-frequency technique where we are just going in and out of the surface with our cantilever, poking in and out. This is in contrast to tapping mode, also can be called dynamic mode, intermittent contact mode, AC mode, amplitude modulation mode. This is an imaging method that is resonant. We are relying on the resonance frequency of the cantilever, and this occurs at much higher frequencies. So fundamentally, a very different interaction mechanism between our force curves and force curve mapping, and then the traditional imaging mode of AFM, which is tapping mode. And thank you to Greg Hochstad, my colleague. He put these two animations together. All right, so let's go back and look at force curves, the static force curves now in detail. So we went over the approach, the snap-in, then the repulsive contact, and then on the way out, we get stuck in this adhesive dip, and then we pull out. So the two kinds of information that I'm going to focus on today that we can extract from our force curves are first the adhesion energy, which we get from this part of the force curve, which is a pull-off force, and the stiffness or modulus information that we're going to get from this repulsive contact region, part of our static force curve. So these static force curves do contain important mechanical information on your surface. The static force curves are measuring the interaction or force between our tip and sample as a function of z. These static force curves are operating in the elastic regime between our tip and sample. So if we map the stress and strain for an idealized crystalline material, what we can see is as we pull on the material, initially, we have a linear relationship between the stress induced and the strain or displacement or deformation resulting from it. That linear relationship, that linear coefficient, is what we call the modulus. And again, that's the elastic regime. As we keep pulling, we get into the plastic region where now there's a nonlinear relationship between the stress and the strain, and then ultimately we fracture the material. But again, our force curves are operating in this elastic regime between our tip and sample. So we collect our static force curves, and then we use contact mechanics models to model the interaction between the tip and sample in order to measure the modulus and the adhesion or surface energy. Now, the building block model in the contact mechanics model is called Hertzian contact mechanics. Hertz predicted the stresses and deformations that occur when two solid objects are brought into contact with each other. I'm going to review it briefly on the next slide. He developed it in the 1880s, but it is important to note that this is just the building blocks for the contact mechanics models we use in AFM, because The problem with the Hertzian model is that it does not take into account van der Waals interactions that most certainly occur between the tip and sample in our AFM measurements because they're on the nanoscale. On such a small length scale, van der Waals and adhesion become forces that we have to consider. And so ultimately what we can resort to are these newer models called the DMT and JKR model that do take into account the interactions between the tip and the sample. So Hertz analysis, just a little bit of a brief overview on these different models. Hertz analysis was developed in the 1880s where Heinrich Hertz studied the interference fringes between two glass lenses, and he pressed them together, and he derived empirical equations to model the observed behavior. And what he saw was that the contact between two spheres formed a region around the contact that deformed around the center, displacing it by an amount he called delta, and creating a circular contact area that had radius A. So again, Hertz analysis is going to be the building block now for our other contact mechanics models. And so because Hertz does not take into account any van der Waals interaction between our tip and sample, and our tip and sample are not like billiard balls, right? We got attraction, we got repulsion, we got these van der Waals interactions that we need to take into account. We have these two other models called DMT and JKR that can model the interaction between the tip and sample and take into account adhesion. When I teach my course, I have a whole unit just going through the math and understanding all these different models, but I just want to give you a brief overview here. The DMT model in turquoise here, that accounts for adhesion in this area here, right outside the contact area. And so if we look at the force versus distance plot for what a DMT model looks like, if we can see it's shown here. So this part here is the adhesion portion that is modeled right here. That's in contrast to the Hertz model. When we look at the force versus distance on the Hertz model, we see there's no adhesion. The JKR model models adhesion right in the contact area, right between the tip and sample, and its force versus distance plot looks more like this, where right now the JKR can model more significant adhesion than a DMT model. So DMT model is a weaker adhesion than the strong adhesion we can see with the JKR. The practical significance between these two models is that depending on your sample, sometimes you might want to use it, or you might need the JKR model instead of the DMT model, and vice versa. So many samples that have only a little bit of adhesion that you might image in AFM, the DMT model might be sufficient. But for those stickier samples, ones that I tend to work with a lot are rubbers or elastomers. They certainly require a model like the JKR model. The DMT model is not sufficient, does not model them properly, and so you have to be a little bit careful in terms of which model you use to model your force curves so that you can get the appropriate stiffness measurements out. Okay, so let's take a look at some real-life force curves from a sample material. What I have here on the left is a 3.5 micron by 3.5 micron image of an impact copolymer, or ICP. The matrix background here is a thermoplastic, and then these domains here are rubber domains. And so what I'm showing on the right are a force curve from the rubber domain in red, and a force curve from the thermoplastic matrix in black here. And I can immediately see some significant differences between the force curve on the thermoplastic matrix and on the rubber. First, just to note on the what we're plotting here. So we're plotting force in units of nanonewtons versus the tip sample separation, which is in units of microns. What you actually collect is deflection in volts versus Z piezo motion, and you have to do some calibrations and conversions in order to get to a force versus separation plot, but this is ultimately the plot you want to analyze. So straight off the bat, there are three significant differences between these two force curves that I want to highlight. The first is the slope on this retract curve. Compare this slope with this much steeper slope here. Remember, that is the repulsive contact portion of the tip sample interaction, and this is where we get our stiffness information from our force curve. So clearly this has a lower slope, which will translate to a lower stiffness than the thermoplastic, which makes a lot of sense. A second difference I would like to point out is the adhesion. So notice we have a pretty big adhesion gap here in the red curve on the rubber versus a much smaller adhesion on the thermoplastic, which makes a lot of sense. And finally, I'd like to point out the hysteresis between the approach and retract on the rubber, much bigger gap here than on the thermoplastic, and this corresponds to viscoelasticity. So the rubber domains are clearly more viscoelastic than the thermoplastic. Again, not a surprise here. But the point is that from these force curves, just visually, we can really hone in on several key material property differences between them, the two materials, and then we can actually apply the contact mechanics models that we just talked about to try and extract some more quantitative information on these two materials. So these are the individual force curves. What we can do is then collect these force curves over a whole area. And so we can collect a series of force curves now on this different area of the ICP, where each pixel point here, where my cursor is moving, is an actual force curve measurement. And then from that force curve, you can extract these following measurements, such as the height, which is just a topography. And what we can see in this height channel of the force map are several rubber domains. So we have a big one here in the middle. It's showing some topographic deformation because it's softer than its surrounding matrix. And we have these rubber domains around here as well. From those individual force curves, we can measure that adhesive dip and get an adhesion measurement in nanonewtons here, adhesion force, if you will. Not surprisingly, showing that the rubber has significantly higher adhesion than the surrounding thermoplastic. So our rubber domains here, 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 on the side, clearly showing significantly more adhesion than the thermoplastic. Not a surprise. Then we can create a stiffness map using the different models available to us. So again, I'm using as a reference our height map here on the left. What I did here was that I fit each force curve using the JKR model. And I picked the JKR model because I actually know the JKR model is the one that is appropriate for this rubber material here. And by doing that, then I can create a JKR modulus map now, where the Z range is in units of gigapascals. And we can see that the rubber domains, not surprisingly, are showing a much lower modulus than the surrounding thermoplastic matrix. The thermoplastic in this sample is polypropylene. And so when we actually measure the moduli from this image, what we get is a modulus for the rubber of about 8 megapascals and a modulus for the polypropylene of about 270 megapascals. Now the modulus for the rubber coming in at around 8 is correct. The modulus for the polypropylene is incorrect by about a factor of 5. And there are two reasons why the modulus for the polypropylene the quantitative number is not correct. The first one is that actually the JKR model is not the appropriate model to be using for the polypropylene. The DMT model is a more appropriate model. So that's one caveat. But probably the more significant one is we only use one cantilever with a given spring constant to collect this force map. Now the cantilever spring constant has to match what we call the contact stiffness of the material, which is related to the actual properties of the material. For this measurement, I tuned the spring constant of the cantilever to the contact stiffness of the rubber because I want to make sure I got an accurate value for the rubber. But because there's such a large difference of several orders of magnitude between the moduli of these two materials, it means that by tuning my spring constant to the rubber, that spring constant was not going to match the contact stiffness on the polypropylene, and therefore I wouldn't correctly measure it, which is exactly what happened. Again, because there's such a big spread between these two materials, you cannot make a measurement on both of them with a single cantilever, at least not using its first eigenmode. So this is always a challenge in these kinds of measurements on a heterogeneous sample, which spans a large range. You kind of have to pick which material you want to match the spring constant to. And again, in this case, I matched to the rubber and therefore got an accurate measurement on the rubber. Here is another example where I had two rubber samples and they had been cured for different amounts of time. So this one was cured, rubber 2 was cured longer than rubber 1. And what I did was collect a force map on these two rubbers and measure the modulus and adhesion as a function of this curing time. And I could see that the second rubber was stiffer. It came in with a modulus of 4.7 megapascals relative to the first rubber at 3.8 megapascals. And the adhesion showing that the second rubber became less sticky than the first. So seeing these expected stiffening and less sticky as a function of this curing process for the rubber, that I could measure quantitatively with these force maps. And again, it was rubber, and I used a JKR model to fit all the data. So these force maps are used extensively by the biological community to make measurements of stiffness and adhesion on biological materials such as cells, bacteria, DNA, all in physiological conditions. The force curves are well fit by a Hertz model for biological samples, so that seems to work well for their kinds of systems. And you can see you can get very beautiful results. So here is showing a force map overlaid onto the topography with the adhesion measurement and the elastic modulus measurement for epithelial cells. And you can see here a histogram where you can quantify the adhesion and the modulus for this particular sample. For the modulus, this is the modulus of the cell. This is just a background material, so less interesting. And here is another very pretty example of the map of an elastic modulus of the fibroblast cell, showing here again the modulus painted onto the topography. And we can see that the moduli being measured here in general are very soft in the kilopascal regime, aligned with what one would expect for such materials. And the final example is a force map collected on a polybutyl acrylate brush. So here's a pretty high resolution force map showing the height, the adhesion, and the modulus, where the adhesion and modulus were now extracted from these individual force curves collected at every pixel. And then we can do histograms on the adhesion plot, show here, and we can see the different components, map it out by the adhesion in the material. Same with the modulus. We can get a histogram of all the moduli values and then focus in on just the molecular ensembles or try and tease out some of the different components of this brush. So current state of the art in these force spectroscopy measurements, we've had a lot of progress. These force curves have been around since the early 90s, and in 2018 we have significant control of the measurement and the analysis. Right now we can pretty much control all features of this force curve. So we can control separately the parameters for the approach, how fast we come in, the retract, how fast we pull off. We can add in hold segments here to do creep experiments and other types of experiments. We can have full control over the kinds of triggers. How far do we want to go in before we pull out? And the frequencies coming in and out. So an important side note on the frequency when you want to do these force curve measurements, your frequencies of coming in, of poking, for viscoelastic samples, those frequencies matter. So if you're looking at a very viscoelastic sample like a polymer, you have to be a little careful about the frequency that you're poking at, because the ultimate modulus or stiffness that you measure will depend on that frequency. On the analysis side, fortunately for us, all the main contact mechanics models are now commercially available for fitting. So DMT and JKR, Hertz and Snedden, which is Hertz but applied to a variety of different geometries, are now all standard parts of force analysis packaging, which is great for us users, makes it really easy for us. We don't have to code up these models individually. We also have a very wide range of spring constants commercially available, which is important, especially as I had mentioned before, you need to match the spring constant of the cantilever to the contact stiffness of your material. So for wide range of material, and everything from biological samples in the kilopascals to some stiffer materials in the gigapascal range, all those would require different cantilevers to do these measurements, and we have quite a range available to us now. And finally, speed. One of the challenges that always limited force curves was it was a very slow measurement. If you remember earlier in the webinar, some of the force maps I showed were pixels, like maybe 20 by 20 pixels or 30 by 30 pixels. They look pixelated. And that's because these force maps are traditionally very slow. In the past 5 years, vendors have made significant improvements in the acquisition speed of getting these force curves so that they are either close to or even at real-time acquisition speeds. Real-time acquisition speed being something like a 256 by 256 map of force curves in 5 minutes or so, whereas previously, depending on how fast you're poking, a 256 by 256 map would take hours. So big improvements in force spectroscopy capability. Challenges that we still face with this technique. First of all, I do want to emphasize it is a very useful tool to measure the stiffness and adhesion force in your sample. If you do some of this fast force curve acquisition, you do end up with large data sets. If you can imagine having 256 by 256 pixels where each pixel is a force curve is a lot of data. So that gets into issues of handling these large data sets. Analysis can still be a real hurdle. So real-time analysis on the fly as you're collecting these force curves is still pretty limited in terms of the models that it can be done with. Generally, the approach is that you collect the force curve data and then you go back offline and you analyze it with more sophisticated models or some tweaking in the models in terms of what portions of the force curve you want to fit. For heterogeneous materials, and we saw this on the impact copolymer sample, you may not have all the materials may not fit one model. So if you remember in that particular sample, the rubber was really more appropriate for the JKR, but the matrix material was more appropriate for the DMT model. So you need some ways, especially for heterogeneous materials, to be able to model certain components with one model and other components with a different model. And finally, you do need to have familiarity with this method and analysis in order to be able to implement it well. So that includes factors like understanding your calibrations, understanding your spring constant determination, the parameters that you're running the sample in. It's not really a black box approach. You need to have some understanding of what parameters are going in and what calibrations are necessary so that you can run it effectively. And I'm going to conclude by saying that truly quantitative measurements with force curves are still a challenge because we still have significant uncertainties in our main calibrations of the tip shape. I always say in my courses that the tip shape is the Achilles heel of quantitative nanomechanical measurements with AFM. Very hard to measure it, and even if you can, it will change on you. Also, the spring constant determination. We definitely have some uncertainties in the spring constant determination, so that affects these calculations as well. And finally, our contact mechanics models are simply that. They are models. DMT and JKR are big improvements over Hertz, but there are many materials that I myself have looked at that really neither model is appropriate for. So we're still limited in terms of how well these models fit the material, which will then ultimately limit how quantitative our measurements are. So with that, I thank you so much for your attention, and I would be happy to take any questions.
Okay, thanks, Dahlia. I'd like to thank everybody again for attending today's webinar. And yeah, if you could go ahead and type in your questions, Dahlia will be answering them here for the next few minutes here. And I'll just turn the questions over to you, Dahlia.
Great, thanks, Chuck. How deep do your force curves go? Well, that completely depends on you. So you set what's called the trigger point, or how far in does that force curve go before you start the retract. And that is certainly a parameter that you will probably play with when you're conducting force curve measurements. Typically, you're exerting a load in the nanonewton regime. So for people who do indentation, this is several orders of magnitude below nano indentation, which operates in the micronewton regime. AFM is typically in the nanonewtons regime, but again, you control how hard you poke into your sample. Another question that's come in is what calibrations are necessary? So I mentioned this at the end, that there are two main calibrations that you need to do force curves effectively. The first is, actually there are three, but the third one is hard to do. So the first two are your spring constant calibration and then what's called your detector sensitivity calibration. And you need those in order to effectively convert from volts, which is what you're actually measuring in force spectroscopy, to newtons of force. And then the third calibration was extremely tricky, which is the Achilles heel of AFM mechanical measurements, is that tip shape. The best way really is to stick it into a TEM or field emission SEM and get a really nice high resolution image of your tip. But not everyone has access to that, and that can be tedious. So we have other methods that we can use, but that tip shape is very important. And right now, I would say the community doesn't have a really good way to measure, to quantify that. A couple more questions. So how quantitative is the modulus measurement off of a force curve? What is the error on that measurement? And that, of course, is the $64,000 question. I can tell you that practically, in my own experience, doing force curves and measurements like that for about 20 years now, your best case accuracy, and best case meaning you put a lot of work into calibrations, a lot of statistics, a lot of repeatability studies, best case you're looking at 20%. More practical, under more practical conditions, probably not going to do better than 50%. Of course, it depends on your sample as well. But getting truly, absolutely quantitative measurements off of these force curves requires a lot of work, and it requires a lot of knowledge. You have to be very careful about how you set up your experiment if you're after absolute numbers. That being said, the relative numbers in terms of trends, this material is stiffer than this one's less sticky than others, that it's great at. So if you just need semi-quantitative numbers or trends, the AFM is really powerful for that. Okay, and maybe I'll take a final question here, which is, does the spring constant of the cantilever matter in terms of your force curve measurement? And so the answer to that, thanks for asking, is a resounding yes. It is actually probably the most important parameter in your force curve measurement, is to pick your spring constant correctly. Because if you don't pick your spring constant correctly, you will either be measuring, you will be measuring the properties of the lever. If it's too soft, then you get no sensitivity from your material. And if the lever that you picked is too stiff, then all you do is get sensitivity from the lever. So if you actually want to get sensitivity to your material, which is what you want, you actually have to be careful about how to pick that spring constant. And if you want to learn more about that, definitely come to the course. We do a whole lab and several modules on force curves and how to get the most meaningful data that we can out of this very popular AFM method, but still one that has significant challenges that need to be understood in order to operate it effectively. Okay, Chuck, I think that pretty much covers the questions so far that we have.
Okay, yeah. Thanks, Dahlia. And thanks again for everybody, to everyone for joining us today. And again, the information about the course is up here and available on our website. So we'd be happy to answer any questions that may come up regarding the course and what's covered in it. We'd be happy to put you in contact with Dahlia to answer those. And we hope to see you then. Thank you.